Hello, everybody. My name is Dave, and that's Abby and Zach. Abby, raise your hand. Zach. All right. And anyone who is in my group as well, if you want to be recognized, raise your hand. Okay. All right. So we did the problem that involved the TV. What I want to do is go over exactly what the problem was, and then go over a couple of the ways that we brainstormed and tried to figure out how to solve it. And finally, the future work at the end is going to be some stuff that we thought of, but we just didn't have any time to really focus on. So I pulled this advertisement off the Clipped website. So Clipped tries to make, optimizations of, gearing their advertisements towards the right amount of people. So that picture there has a kid blowing out birthday candles. You want to make sure that that advertisement is not being sent to like really old people or people without kids. So you've seen this Venn diagram before. We focused a lot of our work on the past week on reach, and there was a difference between reach and impressions. Impressions had already been addressed earlier in some of the Clipped work. Reach would be the impressions minus the overlap segments. So you just count the total number of dots in that Venn diagram. You don't count the ones that overlap twice. So we tried to find out some easy math tricks to take out that overlapping factor. Before we go into the math and stuff, and we have this slide here to talk about the terminology and such. So there is in a lot of the coding problems, there's this grid, and this grid is a giant matrix or a tensor if you want to consider like higher dimensions and stuff. And they name the slots based upon the column and rows, such as that the G sub I superscript network. That would be one of the compartments in one of the slots of this giant grid. And that X vector there corresponds to whether or not a placement for an advertisement is made. So it would be 0 if there's no advertisement there. It would be 1 if there is. And the N sub R corresponds to Nielsen data. So Nielsen is I think of it as a panel of people that they collect a lot of data on. And each person who watches an advertisement or a show gets recorded historically, and they represent a fraction of the total U.S. population. And here's an example of what a grid would look like. So you have those rows, and they would correspond to channel and hour. So, CBS, 8 o'clock or something like that. And then the columns correspond to additional factors for that slot. And there's an example of, labeling one of the slots there, G sub I cost, which would be the cost of that advertisement slot at row I. During the past few days, there were two main considerations. One was for ways to optimize reach, that's on the left, and the other one was ways to approximate reach on the right, and they're all interrelated. But the top, this row here, considers some of the code that Clipped already has. And this row here corresponds to some of our new ideas. Oh, yeah? Okay, thank you. So each method corresponds to a certain way of approximating the reach. Early on, we talked about how to get reach exactly, and this is the math for it. It involves the indicator function, or is it the indicator function? Indicator function, and you cycle through each Nielsen participant. This V here. And this cycles through all those slots, and we check to see if V is in each slot, so if each Nielsen participant had been watching that slot there, and we check to see if it's in that set, and then it tallies up that set, and then that second, I guess this outside indicator thing says that if there is more than one here, it sets it back to 1, so we don't consider the overlapping factor. And then that D sub V here is the weight. So if I'm watching TV, I might correspond to whatever 2,300 people who are my age, and whatever my race, my gender, I don't know. All that information is taking into account. So that's the exact reach. It is hard to implement because it's not linear and it's very expensive. So from here on in, we look at ways to approximate reach and how to optimize using those approximations. So the first day, we looked at some of the code that Clipped already had, and these equations are from their optimization techniques for impressions. So they already know how to optimize number of impressions. That number in the box would be the total number of impressions. So something like this on this line here, we're trying to minimize cost, which is this segment here, using some like fudging factors, or what's the exact term for it? Slack variables. Yes, slack variables. So we're trying to minimize this minus this. So we're trying to maximize this, which is the number of impressions per. You can think of it, increase the impressions, lower the cost. And these lines down here are about trying to hit a certain target number of people. And this is still all impressions. This is the code that they have, and our idea, a lot of our idea is focused on altering this. And instead of having this box here for impressions, we find a term that corresponds to a more accurate number for reach. So this is one of the approximations that we made, hence the, whoops, what number is that? There we go. Hence the R sub 1. This is a quadratic term, so we consider a quadratic approximation. And this phi or phi here is a fudge factor that we haven't really explored too much yet. This term here is tallying up all the impressions, and then you can think of that second term as a penalty term. And we made the assumption that if you have two shows and they're further apart, there's going to be a higher probability that the audience viewing the shows further apart will be different people than if they were like right on top of each other. And this gamma here is 1 over the mean channel switching time. So the average time it takes for some person to change the channel. And this here corresponds to a relationship between channels. So if you're on the same channel, it's going to be a stronger probability that's the same person. They're just going to watch the same channel. And if it's another channel, there could be another factor there that's going to be lower. And okay, so that was the one approximation for reach, and that was like an exponential decay. This one is more rigorous and uses some math. This is an average of all the overlaps, and then we take a ratio of all the averages, and we set this delta H, delta D, and N. So delta H is the change in time between two time slots. We're going to hold that constant. And the delta D we hold constant, and the Nielsen, the network is the N. So the same network, same change of hours, same change of day. So we look at the grid, and everything that's 2 hours apart, we tally up the overlap ratio, and then we average that, and then we use that to get this I. And this I we use, that's the average overlap ratio. That's the number of people. So we're going to get a good guess at what the overlap would be. And that would we would take that out of the total number of impressions. Okay, this is you, Abby. There you
go. The second part was to be in the linear programming framework and still modify certain things. So if you think about it, why do we lose reach, right? Why does the reach is we lose reach because we have repeated viewers, right? The same person is watching the same show one after another. But if you want to cluster viewers, it's a very hard problem. Even if you cluster viewers, you cannot recommend a certain schedule, right? Because viewers have a freedom to watch whatever they want to watch. But we have some freedom in choosing where to place the slots, right? We can control these ad slots. So the assumption we make, which is a reasonable assumption, is to say people watch shows that are similar to each other, right? So if I have some understanding of relationship between slots, maybe that will help me to understand how this overlap happens and how I can minimize it. So the idea is find a way to group similar shows together and distribute the ads on this diverse number of shows. Okay. So just to see some schematic, here you have 3 clusters, and these clusters are made, if they come from the same channel, if they have the same type of movies or shows, or if they are aired next to each other, and based on that, you have some 3 clusters. So if you see the cluster on the bottom left, you have only 2 shows there, and if I pick an ad slot there, I should probably promote it in my linear program, right? Because chances are, if I pick a slot which is coming from a small cluster, it's good. It doesn't penalize my reach. If a slot is coming from a big cluster, chances are I can pick the reach from another set in that set, right? So I should penalize a slot coming from a big cluster. Okay, so that's sort of the idea. So remaining in this framework, what we do is you cluster all these ad slots into appropriate number of clusters. You could use any type of clustering, for example, k-means clustering, and we map every ad slot into some cluster number, into different clusters, and every time you have this linear program, you want to promote small clusters, and you penalize large clusters. So this will depend ideally on the cluster size, the cluster diameter, and the distance between clusters. Here, for example, I have one choice where it's basically mathematically capturing what I have in the previous slide. If I'm a slot in a small cluster, I get promoted. But at the same time, we don't want to penalize large impressions, right? We don't want to penalize every time large impressions. So the second factor, gamma k here, says I want to promote small clusters, but every time I pick a big one, I still want to not penalize it that much. So this is still remaining in the linear programming framework that Clipped already has, and modifying these coefficients so as to promote reach in some heuristic manner. There are some challenges, however. One of the challenges is we need to identify attributes to do the clustering. What are good attributes to do slot clustering? We have some idea, but we need to find more attributes. Given a point from one cluster, how do we put this weight? Maybe use previous historical data. Another question, which is a question you ask every time you do clustering, is how do you determine the correct number of clusters? And so this is sort of the idea of clustering that we explored for this problem.
So the attributes you're using right now are like channel and genre,
yeah. The time they aired, how far they are from each other, and so on.
Are you using viewership data or historical viewership data as well?
Those we haven't. So far, we're just doing genre, the time they are aired, the channel number, and so on. Hopefully, we can include that in the future. Yeah. So next, what happened?
Do I need it?
Okay. So I will hold off on the handheld mic. Another approximation that we used for reach was the idea of pairwise collisions. So we look at the historical Nielsen data to determine what the overlap is for various time slots. This Nielsen data is approximately 1 million rows in Microsoft Excel, each of which, and I think there were about 40,000 unique viewers. So it's a very data-rich set, and it's over, I think, 90 days was the data set that we had. It was aggregated over 90 days. We define a probability tensor, P, where Pi, comma I prime is the proportion of the general population viewers of slot I prime who also watch slot I. So it's a way of measuring the overlap. We give a definition of that on this slide. We do weight it according to the demographic weight that each Nielsen viewer has. N of X is the number of ad slots that were chosen, and R2 tilde is the impressions, the sum of unique impressions at each step. So you can think the first term in this sum would just be G sub I sub K impressions. The product would just be 1. The next term would be G sub I sub 2 times the probability that they did not appear in the first times the probability that these viewers did not appear in the first group of impressions. G sub 3 is the probability, it's the third set of impressions times the probability that they were not in either the first or the second group, and so on. And P in this context is determined from historical Nielsen data. We use impressions, G sub I sub K imp. That is provided by Clipped as a forecast of what we expect to get at a future date when the advertisement is aired. We implemented this using a greedy algorithm. So to start off, we defined some notation. C sub I sub K is the cost of slot I sub K. Capital C is the accumulated cost of the slots that you've already chosen. L is your budget limit. S naught is the set of indices of all network time slots in your grid. And S is the remaining slot choices that you have as the algorithm progresses. At iteration K, we select the slot that maximizes the additional reach per cost, and we give a mathematical definition of that below. At the first iteration, note that that product is 1, so you're just maximizing impressions per cost. At the second iteration, you're maximizing new impressions per cost, and so on. And we terminate whenever the accumulated cost exceeds the budget limit, and we do not use the slot that would have caused you to go over the budget limit. So we terminate immediately before the budget limit is exceeded. Here we have some pseudocode to give an idea of how the implementation of this would roughly look. You initialize your variables while your constraints are not violated. You continue selecting things that maximize the quantity. You update your cost. You update the set of available slot options, and you set your decision variable for the corresponding slot that you choose. You set that slot equal. You set that entry of the decision vector x equal to 1. One problem that we had in this method is how do we handle constraints that depend on the final schedule that was chosen. For instance, at the end, we want 50% of the slots to be between 3 and 6 a.m., so you might be trying to target some sort of college student population that would be up in the wee hours of the morning. That should say method 1 is a penalty. You add a penalty term in the objective function that penalizes deviation from the target ratio. This is a fairly light penalty at the beginning, and it becomes more strict as the algorithm progresses because you want to force it to adhere to the target penalty. Method 2 is a partition. So you partition the set of slots into D1 and D2. D1 is the set of slots that are between 3 and 6 a.m. D2 is the set of slots that are not between 3 a.m. and 6 a.m. If the chosen slots, as with the previous iteration, result in an undershooting, you choose the next candidate from D1, and if it results in an overshooting, you choose it from D2. So if you're under, you choose something that would raise your ratio. If you're over, you choose something that would lower your ratio. We implemented this using MATLAB. We calculated the correlation tensor P from historical data that Clipped provided. We then implemented the penalty and partition methods to accommodate this relative constraint in MATLAB, and the plots. Let me see if I can work this thing. Which one is the? Whoops. There we go. So the black solid line is the impression ratio for the partition method. The dashed black line is the budget ratio, so that gives you an idea of how far along the algorithm is. And the blue is the same deal, but for the penalty methods. So we can see that the penalty method uses fewer iterations, but it has some sort of wild behavior at the beginning. And we also see that the runtime is higher for the penalty method, and it results in lower reach. So the partition method is not only more computationally efficient, but it also results in higher reach. And these reaches were calculated using the pairwise collision method that we talked about earlier. And this was using a target ratio of 50% and a budget limit of $20,000. The reason why these runtimes are so different is that in the penalty at each, as you iterate through the list of candidates, you have to compute the penalty at each step. So that drastically increases the runtime. Future work, one idea that we had was a separation heuristic. So is there a time delta after which the majority of the impressions are new? So if you separate the ads sufficiently, most of the impressions from the later ad should be new. If you have an ad at 6 a.m. and an ad at 10 p.m., they're probably going to be fairly different target populations. We also would like to investigate optimizing more general aspects of the exposure distribution other than raw reach. One thing that Marco talked about on Monday was getting a frequency distribution. That's kind of the holy grail of advertising. Rather than raw reach, you'd like to say, we want this many people to have seen the ad one time and another proportion of people to see the ad twice and 3 times and so on. And we also would like to extend it to multiple objectives. So a primary objective would be to reach 18 to 34-year-old females, and we would also like to reach nurses at the same time. Some acknowledgments and thank yous. We would like to thank NJIT for hosting this and providing us with all of our snacks and lunch over the week. Clipped for providing a very fascinating problem, the NSF for their support. We would also like to thank Peter Kramer, Chris, Yuri, and all of the faculty and postdocs on our group for their help. And we'd also like to acknowledge our team motto, Rafflehuff, which is reach only for low-hanging fruit. We had limited time, so we had to optimize subject to a time constraint. And there are some references that we used in our work. So, thank you.
So are there any burning questions on this problem?
You don't have to hand me the mic.
It has to be picked up here.
All right. So I just had a question about how realistic these partition coefficients are. I mean, partition constraints. I mean, you would think it would be, I want no more than half between 3 and 6 a.m. or at least half between 3 and 6 a.m., which would make it a much easier problem than I want exactly half between 3 and 6 a.m.
Yes. So the way that we coded this up, it was sort of a soft constraint rather than a hard constraint because we did, so let's return to the plots. It's never exactly at 50%, so there is some slack here because the penalty, you're not requiring it to be at 50%, you're just penalizing it if it deviates, and the same for the partition. Yeah, we didn't investigate adding like a hard constraint to the...
But if it was less than or equal to, it's fairly trivial to generalize your output. If you're above, you choose one that brings it down, and if you're below, you choose higher.
Sure. Yeah.
Right. It's something that would be easier. Yeah.
Can you repeat the comment to the mic?
We did this one specifically because this is something Marco mentioned that they were specifically interested in.
And who is this question for so that we know who's...
Well, first of all, just a general comment. So I'm representing CLIP today. So I want to thank all of you for doing such a great job. I think it was very impressive. I'm still kind of digesting what you just presented today. So but definitely a great piece of work here. So my question then is, if I'm following this correctly, you guys have worked on 3 different solutions. Is that right? Like the algorithm you present in the end, is that an implementation of the first 2, or that's the third one?
So there were 3. Oh yeah. So let's go back to the. There we go. Yes. So the first option is impressions only. That I believe is what Clipped already is doing. The second option is the quadratic objective function, and the third option is the pairwise collision greedy algorithm that was presented at the end. Sorry, yes, clustering too. I forgot about that. So there are
It's
4.
interesting to see that I think some of these ideas are also what we have been thinking about and trying to work it out. So it's very interesting to see. I feel like you guys are definitely, thinking in the same direction. That's definitely a good sign. And regarding the first 1 or 2, so I know you guys presented the ideas behind that. Were you guys able to actually implement and see how well it performed? Like with the third example, the greedy search algorithm. Question for Dave, I guess.
So I know Abi wrote a code for the clustering, and I know Zach wrote a code for the greedy algorithm. I'm not quite positive the other 2 had been implemented yet. We just have the theory for them, unless, I don't know, does anyone want to speak up? So yeah, how far along did you get on the clustering? Is it?
So I take a certain set of attributes and go through the data and do clustering. That's as far as I went in trying to see the relationship between the different clusters and different clusters.
Yeah, I'm just so excited because I
Yeah.
think all this is great to, being achieved in the past couple of days. So I guess I'm looking forward to hearing and learning more about what you guys have come up with. So thanks again.
And then I heard you had a drawback of having everything in R or something like that. I don't believe we have any working code in R right now, but hopefully in the future, I don't know. I don't know if we have any aspirations toward learning a new language.
Well, I don't think the tool is a problem. I think the idea is what we're really looking for. So I think I look forward to working more with you guys. Thanks again.